All right, folks, these are the answers to um, number one for the combination circuit problems. And the first thing you need to do is, okay, why is this not working? Um, find the total resistance. So we're going to combine the 9 and the 1 together into, you can just do that in your head because they're in series, you add them. So you have a 10 ohm and a 5 ohm in pure parallel with each other, and then those two are lumped together with a 3 ohm. And then we're going to combine the 10 and the 5. 1 over R tote equals 1 over 10 plus 1 over 5, which is 0.3. So that's 1 over R tote. So that means R tote equals 0.3 to the minus 1, which is 3.3 repeating. Which makes sense because it's less, find the smallest resistor. The smallest resistor is 5. This is going to be better than that. So it's 3.3. So you get a 3.3 repeating ohm resistor and a 3 ohm resistor and a 10 volt battery. And these, well, I'll just draw it real quick. And then that is equal to 6.3 repeating ohm resistor. Okay. You could have, if you want to be lazy, clever, and attractive, you can also, you could also say R tote is a 1 over 10 plus 1 over 5 to the minus 1, and you'll get the 3.3 repeating straight out. So I'll do that next time. All right, so that's the total resistance. The next question says, find the current in every resistor and label it on the diagram. So what's a little bit confusing is we want multiple currents, but you're always going to start with the total current because that's where all these subcurrents come from. So the total current coming out of the battery is V over R tote, which is why we found R tote. So it's 10 volts over 6.3 repeating ohms. And that comes out to be 1.58 amps. And depending on, you might get slightly different numbers because it's actually 1.588. So if you kept more sig figs, your numbers are going to vary a little bit. Okay, so then that's what's going through this single loop circuit. So go back to this next loop and then go back even further and you say, all right, there's not really a 3.3 repeating ohm resistor. It's really 2. So we're going to have to use our reverse percentage trick to figure out how this splits. Clearly twice as much goes through the 5 ohm as through the 10 ohm, but then it recombines and joins up again. So we know that this 3 ohm resistor has 1.58 amps going through it. Okay, but we have to figure out what's going through these two and the 5. So I'm going to do that down here, but I'll move back and forth. Okay, so this is when we use the reverse percent trick. So the current through the 5 ohm is going to be the opposite ohm over the total ohm as a percent, right? Because the ohms are going to cancel, times I tote, which is 1.58. So what you get is the current through the 5 is 10/15 of the whole current, which should make sense, right? That's getting the majority. That's getting 2/3 of the current, which is 10/15. And so that comes out to be 1.053 repeating amps. So let's go back to the circuit. That was the current through the 5. So the current through the 5, we now know, is 1.053 repeating amps. To find the current through the 9 and the 1, you could just say, I know the current's got to add to 1.58 amps. So let's just subtract the difference. But I think it's better to do out the calculation, and then we can check our work to make sure that it adds to the total current. Okay, but totally fine if you subtract, this value from 1.58 because you understand that the current is conserved. Okay, so the I through the 10 is the opposite resistor, the one we don't care about, over the total, which we already knew was 15, times the total current. So 5/15 is 1/3. This has 1/3 the total current, which comes out to be 0.527 amps. Oops. A little bit over half an amp. So that's the same current going through both, because if you go through the 9, you got to go through the 1 to get back, in line. So this is current through both of these is 0.527 amps. All right, that is the current in every resistor. That is question B. And you can check your work. 1.053 repeating plus 0.527 amps adds back to 1.58 because the current comes around, some goes this way, some goes that way, and then it rejoins. Okay, and then we want to find the power of each bulb. This gets a little tedious, which is why I think I only put one of these questions on. Because once I know you get it, that's pretty straightforward. What I want you to think about, though, the power equals I squared R. There's multiple currents, but only the electrons that go through the 3 ohm light bulb can generate light. Only the electrons that go through this 5 ohm light bulb can generate light for it. So you want the individual current, not the total. You want the individual current that aligns with the individual resistor. Okay, so that is going to be the power through the 10 is 0.527 squared times 10, or 2.78 watts. The power through the 5 is 1.053 repeating amps squared times 5 ohms, or 5.55 watts. The power through the 3 ohm is 1.58 squared times 3, or 7.49 watts. Okay, so that's the wattage of each bulb, and then clearly the bigger the wattage, the brighter it is. So the moral of the story is only use the individual resistor and only use the current going through that light bulb. Okay, so then this is how quickly the battery is giving energy to the system, and since energy is conserved, they better be the same. So this is the total current, because the battery has to give energy to all the electrons. So the total current was 1.58 amps, and the voltage of the battery is 10 volts. So the battery is giving away 15 joules per second of energy. If you add these 3 things up, I get 15.8 watts or joules per second. So again, good way to check your work, that the energy produced by the battery has turned into, it's all accounted for, it has turned into light, different wattages of different light bulbs. All right, that was question number 1.